So today, we've got another problem-solving excerpt from our Physics 132 class on the Biot-Savart Law and using it to solve the problem of a magnetic field around a long straight wire. I note that this is really dominated by what goes on with the math. The physics has a lot of depth to it, but not such heavy calculation. It's the math that I'll have to spend a bit of extra time on. When this came up this semester, spring 2012, it was on day 30. You can look at that on Blackboard if you want more context for it. The day was mostly spent discussing getting magnetic fields in different configuration of current carrying wires. Before we had gotten to this problem, we had mostly dealt with Ampere's law. And with Ampere's law, we discussed just a bit of how you need a lot of symmetry and how important that is when you apply Ampere's law. The biggest application we had done was the magnetic field around an infinitely long straight wire. Same problem we're going to do with the Biot-Savart law. With Ampere's law, we had also put it in the context of finding the force between two infinitely long straight wires. And after that application of Ampere's law, we introduced the Biot-Savart law and wrote down what it was and how it could be used for a more general calculation. And that's what we're going to work on again here. So, the long parallel current carrying wires, infinitely long, in the ideal case, realistically, very long. We did this together on the blackboard, and by that I mean the real physical blackboard in the classroom. The result we got gave us force per unit length proportional to each of the currents, the current in the first wire and the current in the second wire, and inversely proportional to the distance between them, which we had labeled A. It had constants of nature, U0, permeability of free space, over 2 pi. And again, that was force per unit length because these are infinitely long wires. When we introduced the Biot-Savart law, I called it an analog of Coulomb's law. It's analogous in the sense that it has this 1 over r squared, and it depends on the current, where Coulomb's law depended on charge. And in the formulation of Coulomb's law that applied for electric fields, you only had one charge. Here I've got magnetic field, and I've got one current. I've got constants of nature, and I've got an integral. Because with charge, you can have a point charge. But the definition of current involves motion, so you really can't just have one point. You always have to integrate. You can't have a point current. The interesting thing about this law is that there's a cross product inside the integral. That's not just a times sign, it's a cross product, right-hand rule, all that good stuff. It's a cross product between the differential element of distance and the radial vector from the element of wire to the point you're talking about. Usually we would write limits on this integral and do a specific part of the wire. The most common cases we'll ever deal with usually have either a straight wire or something like a circle where you can actually integrate without much trouble. That's the general law as written there. That's all we really need to start at this problem. First, I better be more careful about saying what the problem exactly is. I have an infinitely long, infinitesimally thin wire, and it's the only thing in the universe. There can be a current in it. I will call that current I, as we always do. I want to find the magnetic field everywhere in space. Since the wire is infinitesimally thin, that means outside of the wire. Since it's infinitely long, I've got a lot of symmetry, and that's what allowed me to solve the same problem before easily with Ampere's law, and I'll mention that again later. But for now, let's do that problem. First, I start with a figure. I draw the wire with a current in it. My very long wire with a current that I've drawn going to the right. I want to pick a representative point, some point out in space, call it P, have X mark the spot. I want to choose axes, and since I want to make life easier and not harder, I choose one of my axes along the wire and another one going right through the point P. Now, before we had all of the formality of Ampere's law, we knew that the magnetic field would go around in circles around that wire. So it's going to point at that point P out of the page along the axis that we would call then Z. But I can't draw on the page because it's a two-dimensional figure. So I got my X and Y axis, I've got my point P, and I want to write down the law, and I want to label everything I need. So I pick an element, ds, along that wire. My ds corresponds to a dx because I chose my x-axis along the wire. The vector ds has the unit vector x hat with it, but I've just drawn in the figure the ds. The distance between that ds and the point P I label r, and the angle between the wire and that radial vector I call theta. Now I'm going to be ready to do some math. So I copy this figure over, and then I write down the formula I need. It might seem when I start, I've got this r and theta, I've got x and y, I've got this parameter a, that's how far along the y-axis P is. It might seem you want to switch to all Cartesian coordinates because you know those are usually easier to deal with than radial coordinates are in theta. But let's watch out. Let's look at the formula. Copied over the formula from a previous page. It's got a ds, which is the same thing as a dx, but it's a vector, so it's got an x hat crossed with that r hat. So I've got mixed Cartesian and polar coordinates. So it looks a little messy. Note, though, that dx crossed with dr, that's going to give me a z hat, right-hand rule, perpendicular to x, perpendicular to y. That's going to be along z or minus z. And the right-hand rule tells me that in that order, it's just z hat. The cross product has a sign of the angle between vectors. So that's the sign of the thing I called theta here. And I've still got the dx. So I do have a sine theta in my formula, in the numerator. There's a theta in the numerator, there's an r in the denominator. I still have a dx, so it's still mixed, but I might want to think about converting to the polar instead of the Cartesian coordinates. Let's try that idea. Stick with the trig for now, the polar coordinates. So I copy over the formula again. I've put what I know so far, that numerator. The denominator, well, r is a over sine theta. Okay. That's simple trigonometry from looking at the figure. That means I've got a theta in the numerator, and in the denominator, I've got an a over sine theta squared. Well, 1 over sine theta. That's tricky. Sine theta dx. Well, if I let x be minus a cotangent of theta, because that's what it is in the diagram, just looking at the trig. I want to get the differential, the dx. Well, dx, d by d theta of cotangent of theta. Oh, you can look it up, you can remember it, you can try to figure it out. One way or another, you're going to get that dx is going to be cosecant squared theta, d theta. The a hangs along for a ride, and the minus sign goes away because of the rules of calculus and what that differential is. Doing the calculus didn't really require you to remember the trigonometry of what cosecant is. Yes, the derivative of cotangent is cosecant squared, but you have to remember that cosecant is 1 over sine. And oh wow, look at the denominator there. So I put all those pieces together, and what I'm left with is a sine theta in the numerator. I pulled the 1 over a out in front, and I've got an integral from whatever angle I start at to whatever angle I finish at, because I need a definite integral of sine theta d theta. Even I know how to do that one. Integral of sine theta is going to be cosine, right? well, almost, it's minus cosine. I stick in my limits of integration, theta 1 and theta 2, for whatever angle I start with, or whatever angle I finish with. The minus sign, again, that's from the integration. Got the 1 over a, that was from doing the trig and pulling something out front. The rest are constants as far as the math is concerned. Now I have to figure out what those limits are. In the case of an infinite wire, you start at a really, really small, that is negatively infinite, value of x. That would correspond to theta being nearly 0. In fact, in the limit that x is negatively infinite, theta is really 0. When you go to the other end, theta has opened up completely, it's pi. Watch out, in that expression I wrote, theta 2 comes before theta 1. So the cosine of pi, which is 1 with a minus sign, minus the cosine of 0, which is 1 with a plus sign, gives me a negative 2. That negative cancels the negative in my formula, and I'm left with the magnetic field being z hat, constant of nature times the current, over the distance away from the wire. This is something we got from Ampere before, and it was noticeably harder to get it here, but I claim it's worth doing for a couple of reasons. First of all, we've now had a very non-trivial example with the Biot-Savart Law. Second of all, it gives me a chance to talk about that result again. That result should look familiar. I have something that's very long and thin, and as I move away from it, the field drops off as 1 over distance from that long, thin thing. I claim that this should remind you of some example with electric fields and charges in a particular configuration. Go figure it out if it doesn't pop into your mind. Another thing I have to say about that, even though I got the example, the same answer from Ampere way more easily, it only worked because I had to invoke these symmetry arguments about being infinitely long, knowing that everything was rotationally symmetric and translationally symmetric, and being able to flip it around. There were a lot of arguments that went into it. This calculation worked even if the wire had finite length. I did not have to assume anything about symmetry of space. In fact, I could change that into a problem where the wire was finitely long and find the magnetic field due to that finite section, as long as I can calculate these angles, cosine theta 2 and cosine theta 1, that go into describing where the point is. So this is a much more general result and a much more realistic result, because real wires are not infinitely long. So I've got the same result from Ampere and from Biot-Savart. Ampere's law was way easier, just like Gauss's law was way easier to use than Coulomb's law. Ampere's law required a lot of symmetry, just like Gauss's law does. Do be careful, there is such a thing as Gauss's law for magnetism, and it's not like Ampere's law. It's quite a different law. We're going to run into that soon, but I wanted to bring up this thing about looking for how you calculate something when you can apply different laws, and the mathematical analogs of when something's easy in a symmetric situation versus something that's hard but you can apply any given time. So this is a tip to some of the stuff coming later that's going a bit beyond this problem. This problem is probably not really as hard as you thought, was it? See you next time. Have fun.